You were kind of close.
Yeah, the 20th is on Friday. It's my grandma's birthday.
Ooh. Then what? 7 always. It's my favorite. This will be the last thing that we learn in regards to this particular topic. So you can expect today, the notes will take a little time, and then tomorrow will be just a complete work day. So any remainder of the time today will be work time. And then, of course, the whole period tomorrow will be work time. And then you can expect a practice quiz on, I think I put Monday on Canvas. I'm not really sure. But so this will mark the end of this topic. We're not done with polynomial functions, but we're done with this aspect of it for now. So after we learn this today, then you'll kind of have all your information, zeros, end behavior. What did we add yesterday? Oh, yes, of course. Thank you. The positive and negative intervals. And then today we learn about multiplicity. And then those 4 facets all put together make us pretty mathematically powerful when it comes to sketching the graph of a factorable polynomial. So after this quiz, then next week we start looking at polynomials that aren't conventionally factorable. And we have to learn this thing called the rational root theorem. And then we start attacking polynomials from a much more mathy perspective. The graphs will still be there, but there's a ton more mathy new stuff on the front end. So for now, this is it for today. So I have 3 examples carefully concocted, and then I do have an assignment that'll be on Canvas here in a little bit. So we're gonna start with this. And I'll explain what that word means once the word up at the top of the board there that new word. Sorry, there should not be a 3 there. I shouldn't talk while I'm writing. So let me get this out first. There we go. So that word up at the top, that new guy that you see is going to be the focus for today. Super easy lesson if assuming, again, as always, that everything to this point has gone well, then there'll be no issues today. It's just one new little twist. So what would we do first? For sure. So, and again, I noticed you guys do not talk about end behavior early, and I'm totally down with that. Like, it's really not almost even the right time. So we'll do all of our factoring stuff. We'll get it all set up. We'll make our dots on the x-axis, and then we'll think about the end behavior and talk about that. So I kind of like this approach. So what I've been doing is just getting rid of the f of x equals, and then just substituting it with like an equals 0 over here. So we're off. And yeah, GCF for sure is what? You're fine. So I'm going to pull out x squared, and that's going to leave me with x squared minus regular x minus 2. Thank you, equals 0. Good. And then, of course, we factor, 4th verse, same as the first. So when I factor the white thing down, it's a pretty typical quadratic trinomial. What does it factor down into? X and x for sure. Minus. For sure, we need a minus and a plus. Right, we want the minus to be with the 2x product and the plus to be with the 1x product, so that when we add those together, we get the minus 1x in the middle. So there you go, factoring 101. And then, of course, we find our zeros. And what number makes the red bubble equal 0? Correct. And what number makes the purple factor equal 0? Correct. And what number makes the yellow factor equal 0? Good. And so this is where today's lesson becomes relevant, because we're about to see something, an incongruity. We're going to see something that's not possible, and then we'll talk about why it's not possible, and we'll work our way through why it's not, and then we'll make it possible. So using all of the knowledge that we have at this point, let's go make some axes first of all. So we need an x-axis. And we need a y-axis. And we need to mark our ticks. Just always be mindful of, what do I need? Don't put too much more than you need. We need to go as far to the right as 2 and as far to the left as -1. And then we're going to mark them with our splotches. I'm trying to be consistent about this. So 0 gets a splotch, boop, and 2 gets a splotch, boop, and yellow -1 gets a splotch. Now comes the point of today's lesson. We're about to see a crossing of two things that cannot be true. So if we go back now, this is the time in the problem when we would go back and look at the end behavior of the polynomial function. So if I go back to the very beginning, what does this yellow number tell us?
But it has the same name.
They're either both up or they're both down, right? The arms of the graph either go up, up, or down, down. That's not up to us. Like that's not up for debate. And then the number in front is a 1, which tells us what? That the arms go up and up. And it's here that you'll see something that is impossible. So based on what we've done to this point, we're going to see that this can't happen. So if I start to construct my graph, you got to bear in mind it's up, up. Like, again, that's not up to us. It's not up for discussion. So if I end this one up over here, which I know I don't have a choice, and I end this one up over here, think about the graph and think about the quandary. If you were sitting here taking a test, you know that the graph has to go down, then you know that it has to come back up, and then you know that it has to cross back down, and you find now an incongruity. You should see that. You should see that this is not possible. So there's two things that are colliding with each other here, and we haven't made any mistakes, but that's where the new guy today comes into play, is one of the zeros has something that we call, here comes that big word, multiplicity. And the fact that do you remember, let's go back up and look at the zeros. And I hope this part makes sense. Focus on the red guy. What's the degree of that factor? The degree. What's its exponent? 2. What that means, pay attention now, is that that 0 counts for 2. It has what we call multiplicity. Technically, if you were to make a full comprehensive list of all of the zeros, this is what they would look like. X equals 0, X equals 0, X equals 2, and X equals -1. This is not, we don't make the rules, we just follow them. And here's the law of the land. It's called the fundamental theorem of algebra. And it states that the yellow number up here is a 4. It means that without debate or negotiation, this problem will have 4 answers. If we just listed them out the way we have in previous days, we would say there's only 3 answers, right? That was kind of our first conclusion, was that the answers are 0, 2, and -1. But if you just think of it as 3 zeros, then you see that the graph is impossible, right? It can't do that. It can. So here's what you need to learn about multiplicity. How many times does the number 0 count as an answer to this problem? 2. That means it's what we call a bounce root. And I'll show you what I mean when I graph this. The graph is not going to cut through the x-axis at the red dot, because the red dot counts for 2. I need to know, are you with me on that? Aren't there 2 answers that are called 0?
Yeah.
Therefore, the graph is going to behave like this. Check it out. It's going to go down. It's going to come back up. It's going to bounce off of that rather than crossing through, and then it's going to come back up. I've left this topic out for the first few days because I thought this would make more sense once we're comfortable with all the basic stuff that comes before it. But look at how the 0 does not slice through the axis at 0, but rather it hits it and bounces off. What you need to know about multiplicity is this, is that if the same answer occurs twice or 4 times or 6 times or 8 times, what do all those numbers have in common? 2, 4, 6, 8. What are they all? They're even. If a root or a zero has a multiplicity that is an even number, then that zero is what we call a bounce root. It means it hits the axis but does not go through. It hits, backs off, and comes back the same direction. That's what enables this to be possible. And so today you're going to start seeing graphs that behave a little bit differently. We know all the math behind the scenes. We know how to set it equal to zero. We know how to factor. But we now start seeing that the same answer can occur more than one time. Mm-hmm.
If it's like, so in this example you said it was two, what if you have one that's like 4 or 8?
No, it doesn't bounce multiple times. I wasn't expecting that question, but I'm really glad that you asked it. Let's go to Desmos real quick and take a look. So I want you to see what happens as a zero occurs more than one time. So let's take, well, here, let's do the one we just did. How about that? And I'm going to put it in as just like it is. So I'm going to do x to the 4th minus x to the 3rd minus 2x squared. So you can see the graph on the board that we just did, and you see it behaving, correct? Watch what happens if I add another, by add, I mean like multiply by another factor of x. Not x, but like Kyla said, let me multiply in another 2 x's. So what I'm going to do now is I'm going to multiply by 2 more x's. And now I've upped the degree of that multiplicity root. So now if you think about the number 0, it occurs 1, 2, 3, 4 times. I've added in 2 more factors of x. It makes it flatter when it bounces. If I could, I'm going to zoom in on this for you, and I want you to see how it's pronounced. It's never technically flat, but do you see how it approaches, and it comes in for its landing sooner, right? So a bounce root with a degree of 2, if I get rid of this, here, let me do a little Control C, Control V. Now, if I get rid of the extra x to the 2nd, look at the different behaviors. So the green one is the one where the bounce root only had a degree of 2. The blue one is where it had a degree of 4. What do you suppose is going to happen if I add another one, but I make it have a degree of 6, give it an extra bit of juice? What's going to happen now? It's going to be even flatter. And if I zoom out, you can see, look, it's still approaching the number. And I know it looks like it touches the x-axis early. It doesn't. If I could sit here and zoom in on this for 20 minutes, you'd see I can keep zooming and keep zooming. And it's technically not touching the x-axis until it gets to 0. But the higher that degree gets, 2, 4, 6, 8, 10, holy smokes, that bounce root comes in for its landing a lot sooner. It tries to flatten a lot quicker. And that is only if it's an even power. If it's a 2, a 4, a 6, or an 8, you found yourself a bounce root. And that's what makes all the pieces fit together. Mm-hmm.
When you do the negative over coordinates, would the second one be 0, 0?
Say again? I'm sorry. I don't know what you meant by that.
Like the positive over with an infinity -1.
Oh, the intervals?
Yeah, that's right. Would you do -1, 0, and 0, 0? And then
no. So our intervals will not change. The intervals, let me get rid of these extra ones so that no, it's still only, it's an interesting thing. It's still only one physical location, but multiplicity gives it more pull. So like if we were going to do the intervals on this one, our intervals would still go right. So our intervals would still go from -infinity to -1, -1 to 0, 0 to 2, 2 to infinity. Great questions. So far, so okay. Okay. Let's do another one. So this is what the graph looks like. And you can see, like, I didn't nail it. As I've said many times, I'm not worried. It's more of a calculus-y concept to really start focusing on how deep are the dips and how high are the tops of the arches. Like the depth of this point and the depth of this point at this point in our education is not our concern. And you can see from looking at the graph that, we missed the mark by quite a bit. Look at how far down that dips. Holy smokes, right? But again, that's not for now. Okay. Let's do another problem. So again, the focus on every problem in the notes today, there's 2 more examples and then a worksheet with 6 problems. Every problem has multiplicity. That is the primary focus of the new stuff today, is to watch out for multiplicity. So our next example is f of x equals negative 2x to the 5th plus 2x to the 4th plus 24x, you probably guessed it, cubed. Yeah, let's set this bad boy equal to 0 first off, and then let's pull out our GCF and get to going on our factoring. So I'm going to set it equal to 0, force the issue, and let's get going. So what is the GCF? Negative 2x cubed. Good. And then we're left with a very simple quadratic, which is x squared minus, nope,
X, just X.
just x. X to the just x. Very good. And then minus 12. So as has been the case, and on this quiz will continue to be the case, is we're going to pull GCFs to expose simple factorable things. Like there's not a lot going on with the factoring. It's all stuff you know how to do from the first month of school. So we're going to have negative 2x cubed, and then we're going to factor our quadratic trinomial down into x minus plus 4, 3, done. Let's talk about the answers. According to the fundamental theorem of algebra, looking at the top of the television, how many answers will this problem have?
5.
It will. We're only going to see 3, but multiplicity to the rescue. So this guy, the red guy, gives us what? What makes that equal 0? 0 is the only thing. 0 is literally the only number you could put in for x in the red bubble and make a number answer of 0. Nothing else would work. However, how many of those are there in the red bubble? There are 3. So when we write this down, we write x equals 0, and then in parentheses, we put times 3. That is your new notation today for how to express multiplicity of a root. We don't put times anything when it's a single root. If it's a single, we don't acknowledge multiplicity. It's a simple crossing root, easy, nothing to it. But the multiplicity of 3 is going to behave interestingly. And then, of course, we got purple guy. What's that? And that's just a single root. So that'll be just a basic normal crosser like we're used to. And then we have the yellow, which is. So I want to head over before we graph. And by the way, this one will not have an incongruity. This one will be graphable as you know it. However, I don't know what order I want to do this in. Let's make our axes first. Let's do this. Let's just get them all set up. So we need a lot of symmetry on this graph. I think, we're slightly less on the left than on the right. So maybe give it a little more love on the left, on the right-hand side. So we need ticks at -1, -2, and -3. And then we need ticks all the way across to 1, 2, 3, 4. And now if I mark with my splotches, I'm going to mark a splotch at 0. I'm going to mark a splotch at 4. And I'm going to mark a splotch at -3. This one, you would be able to graph, but I need you to be aware of how the graph is going to look a little bit different. Based on what we know, going back up to the problem, what is its end behavior? Say again. Perfection. It's high-low. We know that because the 5 tells us up there that they're different, and then the negative in front tells us that we switch to the other one. Instead of low-high, it switches to high-low. And so the graph can behave correctly. We could make this one, but on a test, if we're not aware of what multiplicity is doing, we're going to get dinged because it affects like the visual sort of like the structure of the graph. So could it be a high-low? Let's take a look. Very much so, yes. There's my high right there. And there's my low. Now, according to what we know, and don't do what I'm about to do, I'm about to make a graph that is not correct. I'm going to make this, and then I'm going to have it come up through here, and then I'm going to have it come down. And again, I did not go high enough at all. What?
I did that.
Okay, don't do this because I have to make a modification. What the graph actually does is based on multiplicity. First off, where is the multiplicity? At 0. And so this time it doesn't approach, flatten, and bounce. It approaches, flattens, and crosses. So when I see multiplicity at the number 0, how I approach that coming in and going out is going to be different. So the graph is actually going to look more like this. It's going to come down and it's going to start up a little quicker, and then it's going to flatten here. You see that? And then it's going to stay flattened, and then it's going to regrow like this. Do you see just this little bit of flatness? That's what multiplicity does. And again, going back to Kyla's question or what I said earlier, what do you think happens if that multiplicity goes up from 3 to 5?
It'll just stay flat.
It stays flatter for longer. So like if I change the multiplicity to 5, then this green line that I'm about to draw would be more accurate. If that root had a multiplicity of 5, it's going to head up sooner, flatten for longer, stay flat for longer, and then finish its journey, you see. And as the multiplicity increases, that impact just gets exaggerated. A multiplicity of 7, 9, 11. So what we take away from these last 10 minutes is if the multiplicity is even, it's a flatter bounce root. If the multiplicity is odd, it's a flatter cross root. Got it? So the graph of this one should have a little flatness around the 0 named 1. Let's do another one. So far, does that make sense?
Positive.
The intervals?
Yeah.
Yeah, that'll still be a part of it, but I don't think we need to do that today, right? Like we know there's 4 intervals or, blah, blah, same, but yeah. So no, it doesn't change. Going back to what Mari said, what the intervals are doesn't change. There's no change to that today at all. It's just the structural, like the appearance of the graph.
So what would a normal one that is?
If it didn't have multiplicity, you sure? All right. Right then. Last one. Did you just sigh?
No, I was free.
What do we do first? Let's make this little homeboy equal to 0, and then get rid of the f of x side, and poof, we're off and running. Here we go. After that, pull out the GF like that. Let's pull out that GF. I'm gonna start calling it that every once in a while. The greatest factor. What is it? Negative dose. Good. We can't pull any x's out this time, so we already know this graph is not going to interact with the x-axis at the number 0. The only way that a graph will touch the x-axis at 0 is if you have a commonality of x in all the terms, okay? So if there isn't that, then we know that 0 is going to kind of be out of the loop here. So what's our polynomial that's left over? Mm-hmm. Thing about being a math teacher is you have to think as you teach something, do they know this? You wouldn't have known this 3 weeks ago, but now you know how to factor this. What is this called? It is a lookalike. And when you factor a lookalike, it's not just a normal quadratic. This one's going to have more meat on the bone. So I'm going to leave the GCF out. And because it's a lookalike, I have to think about it like a quadratic, but structure it as a buffed quadratic. Yes. What are my signs? They're both minuses because they multiply to make a positive 81, but add to make negative 18. And then what do we notice? Each of these in parentheses is a what? What's it called? It's a difference of squares. And when I factor down, say, this purple one, it factors into its own cute little batch of x plus 3 times x minus 3.
And then you could.
And look, yeah, there's another one. And so rather than square it, because I don't want to confuse anybody, I'm just going to write it out again. But I don't disagree with that. Now to make this official, let's clean it up. Let's bring down our useless GCF and bring down our equals 0, because remember, 0 is what makes all this work. According to the fundamental theorem of algebra, how many answers should there be? There should. We knew that going into this, that it was a 4th degree polynomial. We're going to find 4 answers. And in this case, I see that this one with the red check mark and this one with the red check mark are the same. What answer does each of them give us? So x equals -3 is a 0, and our notation, remember, is times 2. We just found a bounce root. The ones that I'm circling in red, do you see how they're the same?
Yeah, I see that. I'm just writing everything down.
Okay. And then the ones that I'm going to circle in yellow are the same. The little yellow check marks, yellow ovals, and what do they give us? X equals +3 with multiplicity of 2 times 2. Just a little times sign. Times 2 means there's 2 of them. And of course, you know this, but I have to ask just to make sure. The white box that I just drew, what does it give us? Absolutely nothing. It's trash, right? Remember that GCFs that are just numbers are just, let them flutter away. We don't need them. So let's go take a look at our graph and see what this one looks like. Get our axes squared away, and then we'll talk about end behavior, and then we'll talk about the roots. And I think that's that. So I need an x-axis. And this graph will be symmetric. My zeros are on the same distance away from the center. So I'm going to make a tick at -1, -2, -3, and then make 3 more ticks at 1, 2, and 3. So when I mark my splotches this time, I am going to mark only 2 splotches. Although there are 4 answers, the cat's out of the bag. You get this now. There's a splotch, a mark at -3, and there's a splotch at +3. Let's go back up to the beginning. What is the end behavior of this function? So low, low. And again, good work, good detective work. The order in which you do these is critical. Look at the yellow box first up here. That 4 being even tells us that the arms will be the same type. And then the number in front is the finisher, who says they'll both be down. So the end behavior is finish down, and we can now make that happen, right? And so the way this graph is going to look is we're going to see 2 bounce roots. So we can see that the graph finishes low. I don't actually like that there at all. I'm going to move that a little bit. But what's going to make all this work?
You do it more flat.
Yeah, and so it's going to have a bounce right here. And it's going to have a bounce right here. See it? And then you can complete your graph. So it heads down, and it heads down. And then so in the middle here, it's going to have some like this action going on. And done. So without your understanding of multiplicity, it would have been really easy to miss this graph and have it just go up and down. This would be one where you could get a very wrong answer that feels right if you didn't understand how multiplicity works, right? So let's take a look at that graph. Let's head over to Desmos. Ooh, that's bright. -2x⁴ plus 36x² -100. This one's going to be pretty obscene. And again, look at how far down it goes. 162. Well, I kind of knew that already, but yeah. And I could rescale my axes. If you ever want to play with Desmos, it's free. It's just a website or an app, whatever. But you can screw around with your axes. So like if I took my y-axis and I made it go, um, I don't know, from like negative 600 to 0, and I can get a little bit of a better perspective on it. And you can exaggerate this. The more you play, if you're ever in Desmos, I'd recommend that you use Desmos regularly, because it's going to be a good learning tool. It can be a good cheating tool. It's like photomath. I mean, photomath is the best thing in the world if you know how to use it. And Desmos is the same way. If you use photomath to guide yourself and to check answers, it's a beautiful tool. Never thought I'd say that years ago, but it is a beautiful tool. And Desmos is the same way. If you use it just to copy an answer down to get something done, you're cheating and it's hurting you. But Desmos is huge. It's so customizable and tinkerable and so free. It's so nice. So anyways, that's the notes for today. Do you have any questions on that? So even roots bounce, odd roots, flatten, and cross. Got it? Okay. I'm going to pause this and then I'm going to post your canvas because I don't think I did yet.